Hi, welcome back to the session. This time we'll go to the new chapter called Hypothesis Testing. As we mentioned last time, well, we actually have seen sort of one example about the hypothesis testing was the Coke volume example in chapter 6. That was the case. We have seen that, well, we assume the machine works nicely. Which was the assumption that the population mean of the Coke can be filled up was still 12 ounces. And the mean volume of the Coke filled up was 12 ounces, but what we have is from the population. We get a simple random sample of 36 cans, if I remember that correctly, and we found that the sample mean of the volume was 12.19 ounces. So, well, we can assume that maybe we don't know what it is, but maybe the mean volume was greater, right? That is intuitively right? If we get some simple random sample to find the sample mean is bigger than 12 ounces as machine was set, then, well, from the population we do that, then maybe what we can asking ourselves at least, right? Not conclude yet, but we can asking ourselves that, well, or doubting that, well, the mean volume is higher than 12 ounces. I wrote volume twice. The mean volume is higher than 12 ounces. That's what we can doubt. Then do some math. What we had done was in chapter 6 we found a probability that, well, it is very unlikely to get the sample mean of 12.19 ounces or extreme if the population mean was 12 ounces exactly. Right, so after we do the math, then we could reject the assumption. Or maybe if our probability found out is large enough, we cannot reject the assumption. Right, this assumption was the assumption here. What we had, all the equation, all the question, all the math was based on the population mean is 12 ounces. If something wrong, we found out in this step that, well, it is very unlikely to happen. Right, then we could reject the assumption which states the population mean was 12 ounces. We could reject that. Right? Then whatever we doubting is actually true. Right? So that is what happened in the previous chapter. Right? And well, that's actually a foretaste of what we have for the hypothesis testing. Actually, this part we will go more detail, right, of how we set up an entire hypothesis testing, entire full step of how we do this problem. Well, we have seen that we have the assumption, we have the one with doubting. So based on the doubting was based on was the experiment we got. Right, so let's see the hypothesis. Right, the hypothesis. The hypothesis is a statement about the population parameter. Like what we see, we assume the population mean was 12, or from the experiment what we can doubting is the population parameter may be greater than 12 months. Right? That is the statement about the population parameter. Could be population proportion, could be population mean, could be other things, right? Population variance, could be population standard deviation, etc. Or the population parameter could be the statement about. And what we are, of course, focusing on again will be the population mean. We're just focusing on the population mean. And from the previous chapter, we have seen that, well, the mean maybe followed the normal distribution, maybe some information was missing, it followed the t-distribution, right? So that will be two criteria still. But anyhow, the hypothesis is a statement about the population parameter. Then the hypothesis testing is a standard procedure for testing a claim. Right, so not only get the hypothesis, but also we need to state clearly what we are testing on and what the math means, like doing the math to find the probability, or either the probability of p-value so-called the p-value, or some other way to show it. Then also we need to draw a conclusion of what we are finding, what's the result we're finding. So that is a full standard procedure, which we will see the steps later on. Well, if an assumption, under some given assumption, right, it is extremely unlikely to have a particular observed event, which referring back to the code, right, if the population mean is 12 ounce, if it is also extremely unlikely to have the mean of coke to be 12.19 ounce, like what the experiment we got, or the observation we got. And then we would conclude that, well, the assumption is probably not correct. It might be wrong, of course. It's for someone is extremely lucky, right, to get those particular observed events. It's possible, but most likely it is because the assumption we make was not right. And then, if that happens, we can conclude that the assumption is probably incorrect. Of course, it's not extremely incorrect, or it's not absolutely incorrect. We have just saying probably incorrect. Right, that is a conclusion I can make. That means we will reject the assumption. We will say the assumption was not right, and based on the question, we will see something else. So that is the basic idea. Right? We're trying to say the assumption was incorrect, but still we need to see some terminology. So terminology, or the basic components of hypothesis testing. So those are the components you will see. The first one called null hypothesis. The second one called alternative hypothesis. The third one is called critical value, and the next one called rejection region. These two are together follows the traditional method. And the next one called test statistics, or test statistic, which is, we will see what it is. And then the significance level. which usually called alpha. It's the same alpha you see from the last chapter. Last chapter we had was the confidence level was the middle one minus alpha, and the tail is called alpha, right? Separated into two tails. Maybe could be one tail that is alpha, and this alpha, and that alpha was this alpha, the significant level. And then p-value. And p-value method is another method we use comparing to the rejection region, right? The traditional method. It is, we cannot say it is easier, but it's just different approach. I want to use the normal distribution, it may be a little faster than we use the traditional method. And then 8 is type 1 error and type 2 error. Type 1 error or type 2 error, I believe I had mentioned a little bit about type 1, type 2 error in the chapter 4 when we go to a table of probability. We have mentioned a little about it, then we'll see more detail about the type 1, type 2 error. But altogether are the components we'll see in the hypothesis testing in this chapter. That 8 different components, which these two are grouped follows in the traditional method from the significant level we are able to find the critical value, and the p-value is another method. Right, use the p-value and the significant level is another p-value method. Right, so two methods to do our hypothesis testing. Other things like null and alternative hypotheses, we'll get that from the question. And a test statistics is a computed value, and type 1, type 2 error is just something else about the basic another components. So about null and alternative hypotheses. Null hypothesis is written as H naught, H of subscript or 0, doesn't matter what it is, but looks similar, HO, H naught. Well, we just follow in the book what it say. Right, the null hypothesis is a statement of population parameter. Right, so if we make the assumption, then what we can do is just make the population parameter equal to a specific value. Usually the wording will support the the wording will tell us what the value is of the population parameter. Right, this one actually is what's being tested. Right, so the null hypothesis, what we're doing the hypothesis testing, right, is because we are doubting what happened from an experiment, like still referring back to the Coke volume example, right? We have a volume of the Coke is kind of larger than what it's supposed to be, like a little more, right, than it's supposed to be. Then the factory is doubting that, well, if we keep doing that, we are losing the profit. Right, the wording is called profit. We're losing the profit. We could, if we have 12 ounce, we could sell for $2. If we have 12.19 ounce or 12.2 ounce, we're still selling for $2. Then the extra 0.2 ounces, it's losing the profit. It's lost. Then that is serious. What happens? Then that is what we're trying to test to see if it is actually more or actually doing wrong or maybe not. Right? If it is actually doing not good, but we didn't make the correct decision to change the performance of the machine, then the problem is still there, then it's still losing a lot of profit. Right? So if we didn't make the correct decision to the parameter, then it will be in trouble. Right? So it's a very serious problem. And in the meantime, the alternative hypothesis is denoted as the H of A, right? H stands for hypothesis, A stands for alternative, right? Alternative hypothesis. And the alternative hypothesis is a statement that the volume of a population parameter has a value different from the null hypothesis. That's different from the null hypothesis. It may be bigger than certain value as what we found. It may be smaller than the value of null hypothesis states, or it may be just simply not equal. Always have the inequality sign, maybe one of those, not equal, bigger than, or less than. So that was the null and alternative hypothesis, and was the sign of them. for 3 different tests. Well, for 3 different type of tests, the sign which could be for the null hypothesis is always equal. The population parameter equals certain value was the assumption. Then for two-tailed test, we could make alternative hypotheses that the value of the population parameter is not equal to a value, or maybe the left tail we so-called less than a certain value is called left tail. And if we want to make a statement that is bigger than that for population parameter is bigger than a certain value, is called right tail test. That's 3 different type of tests. What we were focusing on will be the left or right tail test. The two-tail test, maybe we're not going to touch that. We're not going to touch that. The left tail or the right tail test was what we're going to do. That was the null and alternative hypothesis. Right, then the next thing is test statistic. What we're focusing on the population mean. For population mean, this testing. And from the previous chapter, we know that, well, for the population mean, when the population standard deviation is known, the population is normal distribution, or maybe n sample size is big enough, then our population follows a normal distribution. Also, sample mean follows the normal distribution. We could use the test statistic as the z-test. We put a star on the superscript. Which the mean is the mean of the sample mean, and this sigma over radical n is the standard deviation of the sample mean. Right? The test statistic will be the z-score. Also, if sigma is unknown, but of course the sample standard deviation could be found, right? Still, if x is approximately, if the population is normal, or the sample size is bigger, or if the sample size is big enough, then the x bar follows the t distribution. That is what we have seen from the last chapter, right? The t distribution. So we could use t-score. Which the mean is still the population mean as the assumption made. Right? Testing for a population mean, we have to make the assumption. Right? The assumption was made in the null hypothesis. And the standard deviation of the sample mean is S over radical n. Still with degree of freedom equal to -1, right? The same degree of freedom we used from last chapter. So, to be short, right, when standard deviation of population is given, we use z-score. If the standard deviation of population is not given, we use t-score. And of course, the condition of central limit theorem should be satisfied still. The rejection region, as what number 4 was there, a set of is a region, a set set of all values that leads us to reject the null hypothesis, and the critical value is the value separates the rejection region. For example, right, if we have a significant level alpha is 0.05 on right tail, and we do a sample, if we do a t-test, we have a sample of 20. Then we could find the area in one tail and degree of freedom to be 1.729. Then we can find the critical value by the t-table. Right, sample size is 20, therefore the degree of freedom equal 19. Area in one tail is 0.05, which is this area. If alpha equal 0.05, then we can go to the same t-table I provided. The area in one tail is 0.05, and degree of freedom to be 19 to get the value of 1.729. This 1.729 is called the critical value, and this shaded region here is called the rejection region. If I find a t-test is below 1.729, then it is not in the rejection region. If we found a t-statistic is bigger than 1.729, it falls in the rejection region. Right, then we make a decision based on those where they are. Right, that is the traditional method. And traditional method usually we use we use the traditional method usually for the t-test. well, it has two tests, the z-test and the t-test. And the t-test is more convenient to use the rejection region and with the critical value, right? To use them to find the result. So the decision we make is to reject null hypothesis or fail to reject. The null hypothesis, which what we can get from the feeling of the wording. We doing so many things doing the experiment. We first of all doubting ourselves from the experiment, then try to do the math to support our claims. Right? What we are trying to support is we want to reject the null hypothesis. Right? Because we're feeling something was wrong with the original assumption of the population parameter, then we do the entire experiment, right? Then we do the entire hypothesis testing. So our result is support the claim to reject the null hypothesis. If to find out finally, well, it is not that much unlikely to get an experiment like that or to get the observation like that, we are not able to reject the null hypothesis. That is strong to reject the null hypothesis. That is not that strong to fail to reject. Or not like happily accept the null hypothesis because the null hypothesis was the one designed to reject, right? This hypothesis testing was designed to reject the null hypothesis. Or the evidence or the supporting experiment and so on is a evidence or is a full steps to reject the null hypothesis. So that was our purpose, but fail to reject the null hypothesis is kind of not that much we wanted to be happened. Right? So that was the thing. So that's why when we make a decision, we strongly say, well, we are rejecting the null hypothesis, or then not that much strong saying, well, we are not able to reject the null hypothesis. Right, so put this decision make. And we see the two-way table. My two-way table when the row here is true state. Or nature. Over here is the decision. So to read that, well, the true case is the null hypothesis is true, and we are not rejecting the null hypothesis. We are making the right decision. And when the null is false, when we reject it, that's the right decision also. And when the null hypothesis is true, we are not rejecting the null hypothesis. That is called type 1 error. And which pretty much is the alpha here. And when the null hypothesis is false, but we're not able to reject it, that's type 2 error. That is type 2 error. Which usually the type 1 error is a little more serious. Then what we do is try to eliminate the type 1 error, which in the meantime the type 2 error will be increases. We're trying to eliminate that, but in the meantime the type 2 error will be getting bigger. So we're not making it too small. Usually what we use is alpha to be 1%, %, or the 10% are the usual value we use for the type 1 error.